கேக்குதா சார்?
Sir, Nicholas sir, can you hear me?
Yeah, I am here.
Okay, sir.
Able to hear, sir.
Okay. Hi, good morning, Maxine.
Good morning.
Yeah. How are you?
Fine. How about you?
Yeah, I do good. I'm doing good. And now, are you in Berlin? Are you in Jena or Berlin?
Yes, I am.
Yeah, you are in Berlin. Then. Okay.
I'm in Jena, actually.
Oh, yeah, okay. So all your vacations are over. Now, have you resumed to your work?
Yeah, I'm back to work.
Oh, fine.
So this is the beginning of the semester in your university?
Oh, okay.
I mean, this is a question. Is it the beginning of the semester in your university?
Yeah. It's the beginning of the semester here.
Okay.
Yeah. Here, moreover, here the pandemic is subsided over here. So
Okay.
we open, and then students are also coming here. Shukri, madam. Sir, can you hear me?
Yes, yes, sir. I'm hearing your voice.
HOD, ma'am.
We start, sir.
Shall we start, sir?
Yeah, okay.
Yes, sir. Start, sir. Sir, can you hear me?
Yes, ma'am. Yes. Yes. Not from all. We cordially invite you to the 2-week International Faculty Development Program on Advanced Computational and Experimental Research in Physics, Day 4, Session 5. SRM Institute of Science and Technology is one of the top ranking universities in India. Over 20,000 students and 1,500 faculty, offering a wide range of undergraduate, postgraduate, and doctoral programs in engineering, management, medicine, and health sciences and science and humanities. Foreign faculty, flexible and dynamic curriculum, exciting research, and global connections are the features that set XRM apart. Students have a wide choice of cutting-edge programs, including nanotechnology, bioinformatics, genetic engineering, remote sensing, and GIS embedded systems or computer forensics to choose from. Most of these courses are offered in close collaboration with foreign universities. With this small introduction, I would like to invite Dr. A. Nadraj, my colleague, to deliver welcome address.
Yeah, thank you, sir. Yeah, so today is the 4th day of FDP, the 2-week FDP. So the main motto, that objective of that FDP is to enrich the knowledge of faculties through interaction with the eminent personality like Professor Maxim sir, the knowledge sharing will improve the teaching learning process to the student on behalf of the society. It is that it gives me the great pleasure to welcome all of you for the 4th day of FDP on advanced computational and experimental research in physics. On behalf of this SRM ISD, I welcome our today's chief guest, today's speaker, Dr. Maxime Champano, sir, who is the postdoc researcher at the Institute of Applied Physics, Friedrich Schiller University, Jena, Germany. So he is going to deliver his talk in the entitled, that is the volume laser silicon interactions. We are grateful. We are grateful to him for accepting our invitation to share his knowledge as the chief guest. At the last, I would like to welcome all the young researcher, teacher, all the students present here to make this event worthwhile. Sir, we are all very happy to hear you to hear the talk, sir. I welcome, sir.
Thank you very much for your kind introduction.
Yeah. With that, I want to introduce that today's speaker, Professor Maxime Champano, sir. I want to share some of his credential to you. He is the postdoc researcher. He is working in the Institute of Applied Physics, Friedrich Schiller University, Jena, Germany. Professor Maxime received his doctoral degree at Axis Marseille University, France, in the year of 2014, under the supervision of Laurent Lamaitre, Chloé Deschartou, and Jean Ubc. Natoli. His area of research include photonics, optics, and laser, optics and photonics, material characterization, semiconductor device physics, laser, material, non-linear optics. He is also worked as the postdoctoral researcher at the LP3 laboratory in Marseille, France from 2015 to 18 under the supervision of David Crojo from the 2018. He is the postdoctoral researcher at the Institute of Applied Physics in Jena, Germany under the supervision of Stephen Nolte. He has published more than 60 research papers in the international journal. With that credential, we are very happy to hear your talk, sir. So with that credential, I hand over the session to Professor Maxime, sir. Please take over the session, sir.
Thank you. Thank you very much, sir. Can you all see my screen and hear me?
Yeah, you be able to see the screen and be able to hear, sir.
All right, fantastic. So normally, yeah, great. So thank you again for your very kind introduction, and good afternoon, everyone. For me, it's still morning here in Germany. First of all, I would like to thank the organization committee for inviting me to this this session and giving me the opportunity to present you our latest results in the field of laser matter interaction, and especially laser silicon interaction. Whoops, sorry. So maybe you have seen the talk from my colleague Alessandro Alberucci yesterday, which was sorry?
Nothing, you can continue, sir. You can continue.
Okay. Sure. So the talk of Alessandro Alberucci was mainly a general talk, very nice talk, but quite general on the possibilities offered by ultra-fast optics and ultra-short pulses in general, namely in the femtosecond and picosecond regime. Here today, I'm going to speak about in-volume laser silicon interaction. So this is a more specific topic which covers actually a lot of fields, especially in solid state matter, laser matter interaction, and so on. So as it was said, my name is Maxime Chambonneau, working at the Institute of Applied Physics in Jena, Germany. The outline of my talk would be quite straightforward, I would say. So first, I will introduce the context concerning ultrafast laser silicon interaction. What are the ins and the outs, and what can be achieved with ultrashort lasers in silicon? And then I will focus on some recent applications we have developed here in Jena, Germany. First of all, I will try to get my pointer. Yeah, normally you can see it. So first of all, I will speak about optical functionalization of silicon with picosecond pulses. So essentially, this is writing waveguides and optical elements inside the material. Second, I will speak about semiconductor to metal ultrafast laser welding, which was a technique we have developed this year. And I will end my talk by speaking about wafer dicing, silicon wafer dicing, and what can be achieved with ultrafast or ultra short laser pulses for separating a whole wafer into individual chips. So first of all, let's introduce the context concerning ultrafast laser silicon interaction. So as you may know, ultrafast lasers represent an extraordinary tool for functionalizing dielectric materials, especially glasses, but also polymers. And the reason is contained here on the left, because at those ultra short timescales, it is possible to first deliver energy to the electron subsystem, and then this energy will be released well after to the lattice. And this allows, so you have a clear separation between the causes, which are the energy deposition, from the consequences, which are the material response. And it is possible to induce different types of modifications. I will not go into the details, but usually in dielectrics, you can produce some positive refractive index changes or nanogratings, or also some voids when you increase the energy, the incoming pulse energy. So this has a lot of applications for functionalizing transparent materials, and especially some applications are shown here on the right for fiber optics, microfluidics, data storage, micromechanics, quantum computing, additive manufacturing, and surgery, especially eye surgery. So the question now is it easy to transfer the whole knowledge about laser dielectric interaction to silicon and basically do the same? Well, sadly, the answer is no. And there are two main reasons for that. First, there are some technological difficulties, especially if you want to functionalize in volume silicon wafers. As you can see here, silicon is not transparent to visible light, so you will need infrared ultra-fast laser sources. Moreover, you will probably need some optics and detectors, which are more costly and also less efficient in DIR compared to the visible. For instance, in terms of performance, here I give you an example concerning the pixel size of your smartphone, which is on the order of 1 micron. And for the best IR cameras, like in-gas cameras, they are more on the order of 10 micron. But if it was only technical details and technological issues, then it would still be possible to modify the bulk of silicon with ultra-short laser pulses. No, the main problem here comes from physical limitations, and this becomes much more interesting for us, especially when you take a look at the nonlinear refractive index of silicon. It is about 100 times higher than the one of fused silica, which is the typical dielectric material on which a lot of studies have been done. And then this high nonlinear refractive index provokes a lot of optical and physical phenomena, especially a competition occurs between Kerr effect on the one hand, which is shown here in blue, and it is balanced by plasma defocusing shown here on the right. So basically, Kerr effect will have the consequence of a self-collapse of the beam, theoretically to a single point. However, when the beam is focused inside the material, with a very tight beam size, a plasma will be formed. So you ionize the material, and this ionization results in plasma defocusing phenomenon. So you create a population of free electrons inside the material, and this will defocus the beam. So in the end, you will have those focusing and defocusing dynamics near the focus, the hypothetical focus at least. So this is what we call filamentation, which is a highly nonlinear propagation regime. And this filamentation regime has two major consequences. First of all, there will be a nonlinear focal shift, as you can see here on the bottom left. Like for low pulse energies, the beam is focused here, and then when you increase the energy, the focus shift upstream the laser. Second consequence is a saturation of the intensity inside the bulk, which is shown here on the right. So when you increase the energy, well, the laser fluence, so the real deposited energy inside silicon is limited and saturated. And when you take those two consequences together, well, you can conclude that there is delocalization of the energy deposition to the prefocal region. And a consequence of this is that increasing the laser energy will be a bad strategy for hoping to modify silicon. So why should we aim at extending 3D ultrafast laser inscription to silicon? Well, first, because as you may know, silicon is the backbone of constantly growing markets, including quantum technologies, silicon photonics, ultrafast microelectronics, sensors, photovoltaics, and so on. This is shown here. This is growing more and more with time. To date, high precision lithography methods such as SOI, so silicon on insulator, are traditionally used for fabricating silicon-based devices, but those methods usually show important drawbacks as they are limited to a 2D architecture, or if you want to build 3D, then you have to proceed layer by layer. You need a clean environment. It is time-consuming and also costly. On the other hand, laser direct writing has the potential to be 3D, flexible, fast, and contactless. So a pretty agile method for functionalizing the material. To date, for laser silicon interaction, especially, nanosecond laser pulses can be used, and they allow addressing some applications. As you can see here, there is a binary image of the Mona Lisa from Leonardo da Vinci, and this is what can be written inside silicon, and this is the resulting hologram written by nanosecond laser pulses. Well, the main problem for nanosecond laser pulses is that the degree of control is somehow limited by the heat, and the interaction more generally is thermally driven. So I would move to my first topic, which is the inscription of low loss waveguides with picosecond pulses, so the optical functionalization of the material. And this study was mainly motivated by the following question. First, is it possible to write low loss waveguides inside silicon with picosecond laser pulses? we have seen previously that in the previous section that it is quite challenging, but can we find some ways to bypass the physical limitations? Then if it is possible, what is the refractive index change? And third, what is the origin of the waveguiding? So we'll try to answer all those three questions. So for inscribing waveguides inside silicon, we have developed the following arrangement, experimental arrangement, relying on pulses at 1.55 micron wavelength, 800 femtosecond pulse duration, and a few tens of microjoule in terms of maximum input pulse energy. Then we adjust the input pulse energy by means of a half wave plate and a polarizer. So this is controlled optically. Similar, the beam size is controlled optically by means of telescopes, Galilean telescopes in that case, before the beam is focused to the wafer, so the sample, the silicon sample, by means of an objective lens. This objective lens is also part of a microscope working in transmission, as shown here, relying on here represented in green, this light, which allows us to take images of the interaction and monitor the interaction in the XY plane, where Z is often called the optical axis. So here we are perpendicular to Z. Besides, we have another microscope relying on white light emission, an objective lens, and an infrared camera. So we can see through silicon and monitor the interaction in the XZ plane. So what is so you can see here a typical inscription where the bright part corresponds to the current laser focus. So what is the trick we have found for inscribing waveguides inside silicon? Well, we start by damaging the exit surface of the sample, so creating a crater on the exit surface of the material, and then move upstream towards the laser at a constant speed. Here, typically it's 20 micron per second and a few hundreds or on the order of 100 nanojoules for input pulse energy. And then you can propagate and extend this crater, but you produce some strain and permanent modification inside the material by doing so. Besides, we have another arrangement, which is XC2 for waveguide characterization, and this relies on basically continuous light emission at 1.55 micron, which is then focused in the waveguides. So here you can see it's focused to the waveguides, and then we characterize the light propagation inside the lines we have written. First, in transmission, as you can see here, we have an infrared microscope, which enables us to retrieve near-field images. And besides, we have another transverse microscope, which allows us to get, well, some scattered light images. So with this, we have measured single mode waveguides with a coupling efficiency of around 53% and a transmitted power, which is around 25%, which is consistent with scattering images. Like the near-field images and all the measurements in transmission are quite consistent with the scattering images. It is also possible to not limit ourselves to waveguides, but also to Y splitters, which are often called multiplexers. So the idea here is to inject light inside a waveguide and then have two other branches. So the light is splitted, it is split in twice. Here you can see here on this figure on the right that we have a 50-50 Y splitter, which is actually an additional proof of light guiding. And the damping losses are on the order of 4.5 dB per millimeter. Then we will want to characterize the refractive index change of the material. Like normally, if you can inscribe some waveguide, it means that you have a refractive index change, which should be positive most of the time for gradient index optics. And to characterize the refractive index change, we rely first on Helmholtz equation shown here, which allows us to do some simulations of the light that we should theoretically detect. Could you please mute yourself?
Yeah, no, it's some unknown.
Yeah, thank you, thank you.
Yeah, you can continue, sir.
Sir, ask if, sir, you unmuted yourself, sir. So you are muted.
Yes, now you can hear me, I guess.
Yes.
Great. Thank you. So, this method I described previously, relying on inverse Helmholtz equation, is pretty classical. When you take a look at the literature, it's known from the 90s. And besides, we have developed together with my colleague Alessandro Alberucci in this reference 3, another alternative method relying on the overlap integral coupled to a beam propagation method. And with the positioning system we have, which is a piezoelectric stage, we could take some different images when we shift the waveguide with respect to the incoming light and then perform the same simulations. And as you can see, it's working pretty well on this figure. So both methods we have employed allow us to conclude that the waveguides are W-shaped with a maximum refractive index around 2 × 10⁻⁻3, which is in very good agreement with highly confined mode fields. All right. Then one question is, what would be the origin of the waveguiding? So to answer this, we relied on nanoscale characterizations, especially with TEM, so transmission electron microscopy. And as you can see here, it is possible to image some defects, some nano defects along the waveguide track. Okay, what now about electron diffraction? Well, this we have carried out, and as you can see here, there is no drastic change in the crystal structure. So the crystal structure is maintained, but still we see under bright light TEM that there are some defects. So finally, we have carried out recently some annealing experiments, as you can see here. So I will not go to the detail, but the main conclusions of those experiments are, when you increase the annealing temperature, well, the waveguide's properties are degraded, namely the mode field's diameter increases, as you can see here on the right, and the refractive index change decreases. So our conclusion is that the waveguides we have written rely on strain induced by dislocations. So here is the take-home message for that part. With surface seeded inscription, we could write low loss single mode waveguides with picosecond pulses as well as Y splitter with a positive refractive index change higher than 10⁻⁻3. And the written waveguides rely on strain induced by dislocations in the monocrystalline material. So now I will move to my second application, which is semiconductor to metal ultrafast laser welding. So here I will take the industrial point of view, where joining materials is something essential if you want to build complex devices. Well, if you want to do so, then you might use or consider traditional methods such as adhesive bonding, for instance, like using glue to bond those two materials. But those methods usually show some important drawbacks. They may, for instance, require another material or pressure assistance, or they may show some aging or degassing problems, or more often, they may be not resistant enough to high temperatures, which can be a huge problem. Then an alternative was developed to solve this problem, which is called laser welding, which consists of energy deposition at the interface between two materials, as illustrated here. And this provides a fast, clean, and contactless way to join those two materials. This was shown to be applicable in many material configurations, such as glass to glass, glass to semiconductor, glass to metal, polymer to polymer, and more recently, ceramic to ceramic. However, in the semiconductor to metal configuration, there is nothing too convincing so far. So let us have a try. To do so, we will use the following setup illustrated here, and we will use silicon and copper for illustrating semiconductor to metal laser welding. So here, basically the setup is essentially the same, like one laser, one target, and some diagnostics. Here, concerning the laser pulses are around 10 picosecond duration at the same wavelength, so 1.55 micron wavelength, for which silicon is highly transparent. Then we classically adjust the input pulse energy by means of a half-wave plate and a polarizer before the beam is focused to the interface between silicon and copper by means of an objective lens. And this objective lens is also used for a similar microscope shown here, which allows us to do, so this works in dark field, and we can basically acquire some images, some dark field images, as you can see here, and position the focus, the hypothetical focus with respect to the surface. Then we evaluate the bonding quality ex situ by separating the two samples with an indenter. So let us have a try. If we set the input pulse energy to 300 nanojoule, then we are able to measure a shear joining strength of around 30 kilopascal. Okay, good to know. Then what if we double the energy, like go to 600 nanojoules? Then the shear joining strength is lower, it's 10 kilopascal. So this behavior is quite surprising, but the main question is that sufficient for envisioning some industrial applications? And sadly, the answer is no, as in that case, the samples are easily separable by hand. Moreover, the typical values for other material configurations or traditional bonding methods are on the order of 1 to 20 megapascal. So why? How can we explain this? Well, I gave the answer in the beginning of my talk, actually. Everything comes from filamentation. which is what we will demonstrate in the next slides. So those focusing and defocusing dynamics represented here, provoking both an intensity clamping, so a saturation of the energy deposition, and at the same time, some nonlinear focal shift. So here are the solutions we propose. Well, first, in the frame of semiconductor to metal laser welding, we will use an interface with a metal, not only pure silicon, meaning that the absorption should be drastically increased. And moreover, we propose a filament relocation at the interface, meaning that theoretically the intensity, the laser intensity should be increased. But to do so, we need for nonlinear propagation imaging. And this is actually what we did with the following setup, which is nothing else than an inverted microscope working in transmission. And this allows us to retrieve those nonlinear propagation images, so the 3D fluence distribution inside silicon. And moreover, with this kind of data, we are able to measure the nonlinear focal shift as a function of the energy, which is depicted here at the bottom. So here on this data on the right, one can distinguish three different regimes. The first one is at very low input pulse energy, the linear propagation regime, which was somehow confirmed by some simulations that we carried out with the model which was developed recently by my colleague Qingfeng Li, which is open source and thus open access. And if you are interested in doing these kind of simulations, please feel free to note those two references. This might be useful for many applications, actually. Then for intermediate input pulse energies, so back to those data here on the right, between 10 and 100 nanojoules, one can see that the focus becomes unambiguously shifted upstream the laser. However, the shape and the overall shape, I would say, is conserved. And then the final regime is when you increase a lot the energy and go to more than 300 nanojoules. And then one can see that we are in the filamentation regime, especially here for 1 microjoule, where you see those focusing and defocusing dynamics. So the conclusion of this is that when you increase the input pulse energy, the energy deposition will be far from the interface, which is in very good agreement with a semi-analytical model that we have developed, which is represented by the solid lines here on this graph. Okay, so now that we know the reasons for the nonlinear focal shift and we have characterized the evolution of this nonlinear focal shift as a function of the input pulse energy, let us try to push a little bit the limits. Here on the left, you can see that it is represented the shear joining strength as a function of the input pulse energy, so for 2 input pulse energies actually, without in red and with in green nonlinear focal shift precompensation. And it is pretty clear from this figure here on the left that precompensating the nonlinear focal shift delta Z leads to a much better welding. Okay, so what now if we decide to increase the energy even more, but at the same time precompensate the nonlinear focal shift delta Z? Well, the results are essentially shown here on the right with those blue points, and one can see that it is possible to reach megapascal, like more than 2 megapascal shear joining strength with this strategy for around 1 microjoule input pulse energy. And this value of more than 2 megapascal is suitable for applications. Interestingly, one can note that there is no welding possible for input pass energies below 100 nanojoules, meaning that silicon to copper ultrafast laser welding is solely achievable in the filamentation regime, which justifies completely our approach of measuring and precompensating the nonlinear focal shift. Besides, here on the top, one can see that one can see the evolution of the maximum fluence reaching the interface, as well as the energy deposited at this interface, or the energy reaching this interface, as a function of the input pulse energy. And one can here again see that precompensating the nonlinear focal shift leads to enhanced energy deposition. So here is the take-home message for this part. So first, we have achieved the very first semiconductor to metal ultrafast laser welding by characterizing picosecond laser-induced filaments inside silicon. We have measured megapascal shear joining strength that is compatible with applications. And if you are interested in this topic, please feel free to scan this QR code here, which will lead you to our latest paper on this topic published in Laser and Photonics Reviews. Then I will move to the last application, so the last part of my talk, which is entitled Laying the Foundations of Ultrafast Laser Dicing. So here again, the motivations are quite simple. We wanted to answer the following questions. First, is there really no way to modify silicon with femtosecond pulses, like without the help of an interface with another material or by producing a crater? So solely in the bulk. Second, if yes, is ultrafast transverse inscription possible? And third, is it possible to induce some weakening inside the material, so some weak points that can act as a precursor for dicing a whole wafer into individual chips? So to answer all those questions, we have developed the following arrangement, which is essentially the same as previously in terms of optics and techniques we have used, so I will not describe it again. However, we have chosen different laser parameters that are interesting. First, we will use a laser wavelength around 2 micron, not as previously 1.55 micron. Why? Well, the answer is contained here. According to nonlinear propagation simulations, one can see that around 2 micron, there is an enhancement of the energy deposition inside the bulk of silicon. So this is a specific wavelength for laser silicon interaction. Second, we have used sub-picosecond pulses, so femtosecond pulses, but that time with distorted pulses. As you can see here, the autocorrelation trace, one can see that there are a few bumps inside the temporal profile, which can be explained by some satellite pulses near the main peak. And third, we have used a spatial optimization, which consists of counterbalancing the aberrations provoked by the aspherical lens shown here, so counterbalancing those aberrations with the aberrations inevitably provoked by the air to silicon interface. And by doing some calculations with the previous model that from my colleague Qingfeng Li, which is called InFocus, we were able to conclude that around 100 micron focusing depth, there should be some precompensation of spherical aberrations, meaning that the intensity should be maximum near this this position, this focus position. Okay, so what about the experiments? So we have carried out single pulse irradiations, and here are the results in terms of modification or damage probability in the bulk of silicon as a function of the focusing length, the focusing depth, sorry. One can see that it is absolutely non-monotonic, and it is possible to see that it is one can reach 100% damage probability inside the bulk of silicon, so repeatable modifications at focusing depth around 100 to 120 micron. And of course, you need some sufficient input pulse energy, so higher than 1.9 microjoule. So this window behavior shown here was extremely consistent with a nonlinear propagation model, which is developed by my colleagues that I will acknowledge at the end of my talk. And by performing those nonlinear propagation simulations, we were able to see that around 100 micron focusing depth, both the theoretical peak intensity as well as the peak electron density should be enhanced compared to other focusing depth. Finally, we have characterized the modifications by different means. So shadowgraphy, as you can see here, and also infrared interferometry, which allow us to conclude that the modifications that we produced are they consist of micro bubbles inside the material with a positive refractive index change. Okay, so let's try to push again a little bit the limits. And what happens when one moves the sample with respect to the incoming light. So here are the results shown on the left. So it is here I show you that it is possible to do some transverse writing inside silicon. And the line morphology can be discrete, steady, or erratic, mainly depending on the writing speed. So here the input pulse energy is constant at 2.5 microjoule. And we repeated this kind of experiments at different input pulse energies. So here is the input pulse energy on this axis, the writing speed. The black points represent some tested configurations, which allow us to discriminate different domains for the line morphology. And one can see that it is possible to write continuous lines transversely only when the modification probability is higher than 100%. Or well, not higher, but equal to 100%, of course. This means that transverse line inscription inside silicon is intimately correlated with intrinsic breakdown and intrinsic damage production inside the material. And then my colleague Markus Blote has carried out recently some 3-point breaking tests. So the idea here is to inscribe lines transversely inside wafers and then apply a pressure to the wafer. And one can see that from, this is illustrated here on this figure on the bottom, that lines, the transversely written lines can act as weak points inside the material. And when a force is applied, the breakage, the cleaving of the wafer is guided. In comparison, when the wafer is not modified, one can see that if you apply some pressure on the wafer, then it is destroyed in 1,000 pieces. So here is the take-home message for this last part. by using a triple optimization in the spatial, temporal, and spectral domain, we were able to produce some repeatable single pulse modifications. We have also achieved the very first transversely written lines inside silicon with femtosecond laser pulses, and those lines can be used for wafer dicing applications. So, to summarize, as we have seen, in-volume laser direct writing inside silicon is usually limited by filamentation, which prevents the production of permanent modifications inside the material. However, if one uses exit surface seeds, like crater production at the exit surface of the sample, it is possible to perform inscription, laser inscription of low loss waveguides and multiplexers inside the material. Then by taming the filamentation, so measuring and precompensating the nonlinear focus shift, it is possible to carry out some semiconductor to metal ultrafast laser welding, which offers a new avenue for manufacturing and especially additive manufacturing. Then last but not least, we have seen that a space-time spectrum optimization leads to new applications concerning wafer dicing. So this could profoundly modify the way the wafers are diced into individual chips currently. Before thanking you, I would like to acknowledge people actually all around the world in different institutions, both in academia and industrial partners. First, in my group, the group of Professor Stefan Note. So my intern, Namig, my colleagues, Alessandro, Marcus, Jisha, Helena, Qingfeng, and so on. And I would like to also thank the group of Jens Limpert, same institute, so Institute of Applied Physics in Jena, Germany, especially Martin and Tobias, my colleagues who carried out nonlinear propagation simulations, who guide us for the experiments, so the group of Professor Stelios Tsartakis and Vladimir Fedorov, for instance, especially, I mean. People at Leibniz Institute, Kai and Martin, people in the geoscience, the group of Professor Langenhorst, and then people in the industry, so mainly laser manufacturers, Florian Sautiev and Stephanie Tertelmann from Inolas Photonics, as well as people in active fiber systems, which is a company in Germany. Both are companies in Germany. Active Fiber Systems is also from Jena, and I would like to thank Christian Gaida for that. So before ending my talk, I would like to tell you that if you need more information, please feel free to scan this QR code here on the right, which will lead you to our latest works on laser to silicon interaction and even more actually. Everything is open access, and you can contact me directly on ResearchGate, or alternatively, you can directly contact me by email at the following address. So I would like to thank you all for your attention.
Thank you, Dr. Maximi, for delivering a wonderful talk, and your presentation was so colorful and was very fabulous. And really, all the participants, okay, we are gifted to hear your lecture. So very good lecture. We have enjoyed a lot. Thank you, Dr. Maximi.
Thank you.
Yes, sir. So it is in the evening in India. So we are very happy to listen your talk. So it is very informative. The participants who have attended really enjoyed your presentation, and also it gives a clear knowledge about that silica laser interaction, how it overcome the conventional method or conventional drawbacks or limitations. You clearly explained. That was very useful for the participants or the young researcher participated in that event. We appreciate you making time in your busy schedule to accept to share the session on this event. Thank you, sir. It is we are all very happy to listen to your talk, sir. Thank you.
Audience.
Thank you very much.
Yeah, please, participants. So please, if you have a query, so please unmute it yourself, ask. Otherwise, you put your question in the chat box.
Participants, the chat box is enabled now, so you can type your question, or you can unmute yourself and you can ask the question. Dear participants, you can ask the question related to this talk.
We also got a good comment from the chat box also. It is the informative session. Very nice and wonderful presentation.
Chat
Sir.
box.
Thank you.
Thank you all. Thank you. Then if anything is not clear, just feel free to contact me at my email address, or if you have any more questions, that's no problem.
We will share your email address, Professor, and then if anything. Sir, one question just now I noticed in the chat box. Mr. Kannan, he asked, in monocrystalline material, we observe dislocation. How can we rectify, sir? Dr. Maximi,
Yeah.
can you find a
Yeah,
question?
in monocrystalline material, we observed dislocation. How we can rectify by Mr. P. Kannan.
I'm not sure I understand the question. I will try to give an answer. I hope it is right. So in monocrystalline material, when you have some sufficient energy deposition, it is possible to make the crystal planes slide above each other, which is dislocations. So the monocrystalline material is, the material is still monocrystal. However, there is some strain which is produced by this slide up from one crystal plane to another.
Yeah, one more question from N. Radia. If the refractive index is changed, what changes is occur in the waveguide?
Well, if you want to guide light inside a material, so what is a waveguide first? The waveguide is nothing else than a counterbalance of diffraction, especially normally when you focus the beam at the center of a wafer, it diverges at some point. And the waveguides prevents this divergence of the beam. So to do so, usually for laser written waveguides and waveguides more generally, it is possible to induce some refractive index change, which will, so you have a positive refractive index change channel, and the surrounding material is the refractive index of silicon, actually. So the intrinsic refractive index. And then with this channel, at the border of this channel, there will have some total internal refraction. And this leads actually to the waveguide effect. So normally for having waveguides, you need a few 10⁻⁴ or ideally 10 to the minus 3 in terms of refractive index change, and then you have a quite nice waveguide.
Thank you, sir. One more question from the Saukat Hussain. Sir, this work can help to give result on 2D material via computation, like band structure, density of state. Likewise, he is asking.
So it is not too straightforward. It's really another field as far as I know. I'm really not an expert in 2D materials like graphene and so on. I guess it will be hard to compare the band structure of silicon with some calculations of the band structure in 2D materials.
Yeah, any other question, participants? If you have any question, so please unmute it yourself and ask.
Okay. Thank you, sir. Now I request Dr. Jayalakshmi, madam, to deliver a vote of thanks.
Yes, sir. Thank you, sir. So it is my privilege to propose vote of thanks for the fourth day, session 5 of 2-week International Faculty Development Program and Advanced Computational and Experimental Research in Physics 2021, organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram Campus, Chennai. First of all, I extend my sincere thanks to our chairman for his encouragement and support to conduct this 2-week FDP. I extend my warm thanks to our resource person, Dr. Maxim, postdoc researcher, Friedrich Schiller Universität Chennai, Germany, who gave scintillating talk on in-volume laser silicon interaction and enlightened us with his talk. Thank you, sir. I extend my sincere thanks to our director, Ramapuram and Trichy campus for perfect support and guidance extended to us for conducting this FDP. My sincere thanks to our Dean ENT, Ramapuram campus for his valuable support. I thank our VP Academic, VP Admin for their encouragement for this conduction of FDP. I thank all the faculty members, research scholars for their continuous support. Last but not least, I am very much thankful to all the participants who have attended today's session. Thank you all.
Thank you. Thank you, Dr. Maximi. Thank you. Thank you very much.
Thank you all.
Thank you.
Thank you all.
Thank you, Maxime, sir.
Bye-bye.
Thank you, Professor. Thank you.
It was my privilege.
Thank you. Thank you.
Yeah, bye.
Should I leave now?
Yeah. You can leave, sir.
All right.
Thank you.
Thank you. Thank you.
Yeah.
Hope to see you soon.
Yeah, sure.
Bye.
Thank you. Thank you.
Welcome to India, Professor.
I hope so one day.
Definitely.
Thanks a lot. Bye.
Bye.
Bye, sir.